Welcome to Ask and Learn.
Let's show that this series converges for all x. So in part A, let's use the ratio test, where this is our an. So the ratio test requires us to look at an plus 1 over an, absolute value of that, and then take the limit as n goes to infinity. So here we'll have so that's an plus 1 up top, and then an in the bottom. Now we should go ahead and flip that red fraction over and multiply, dividing by a fraction here. So I'll have xn plus 1 over xn, and then n factorial over n plus 1 factorial. So here's a key observation here. If you just look at the fraction, so using the definition of the factorial function, if you write that out, you could see that we could cancel the first n factors, and you're just left over with 1 over n plus 1. So here we'll have just 1x left over, x on top, n plus 1 on the bottom. But here, for any real number x that we have, x is a fixed number. It's not a limit. Here, the n is in the limit, and this will always go to 0 due to that denominator. So you could think of this as being x over infinity, but x is not infinity or minus infinity. X is a real number. So we have 0, which is less than 1, so we conclude that it converges for all x. And that was the majority of the work here, because part B will follow from the test for divergence. So this is a corollary of the test for divergence. So sorry here, mixing up my letters. The test for divergence says if the series converges, then the limit of the an has to go to 0. So that's just a theorem in the book, but in our case, the limit of an, based on our definition of an, this is just the limit as n goes to infinity, x to the n over n factorial. So let me go back and erase that. That's an n factorial there. I'm kind of running out of room here, so there's my n factorial, and then by the theorem above that we're citing, this has to be 0, and that's our deduction in part B, and that completes our answer.